Okay. Thanks for coming. I'm actually a little bit anxious about giving a talk in Google because Google now has very famous name. So today I will talk about part of my research work in school, learning image patch representation for scene recognition from photos, and object tracking, and dynamic foreground background extraction in videos. So I just give you how the problem we are going to try to solve. Fortunately, I cannot show you the original photos in my database. I just show you how rich it looks like. So on left side is indoor, on outside is outdoor. So people can easily tell. But but from a computer point of view, actually the background on the left actually in a local scale image scale space, it's used to confuse with some kind of sky. And on the right side, the red brick wall actually you can also have it in indoor. So it's kind of confusing for computers. So the next problem, it seems different, but actually I will later on show you it can be solved in the same framework. So how do you think it's difficult or not? Like if you're going to task, what kind of technique we're trying to try to use to solve the problem, to track the a human working in this case? I'm not sure it's, I just want to make sure it's not a naive problem. So this video has some difficulty because the lighting conditions are also some kind of contrastness between foreground and background, and also the people you're working. So it's, you cannot have a fixed template and then you just try to search the fixed template. And also you may think, okay, the camera is fixed, so maybe I can detect the background and just with some kind of naive subtraction, we can find the foreground. But actually the two moving objects, at least, there are two people working and the car moving in the video. And also, even in this case, because the low contrast between foreground and background, it's not easy job. So on the right side, I'll show another sequence. It's captured by the handheld camera. So camera is not static, so you cannot use the background information. And also, the two persons have some kind of occlusion, so I think it's a hard problem, at least for computer vision people. My philosophy to try to solve this problem is based on two parts. First is the suitable image representation, and I believe if we can find a suitable image representation, the computation algorithm can be very simple. The combination of these two things actually can solve non-trivial problems. So this is the roadmap of my talk. I will, in this talk, I will just talk about what we think the problem and what's the idea we want to solve the problem, but not too much focus on the implement details. But you can ask me the question over there. So why mini patches? In computer vision literature in the last 2 decades, it's a long history for feature flavor kind of algorithms. So one of the most famous feature is Hertz feature, which is basically corner features. So find the local region, you want to find there are two gradient directions. And now will be very famous shift features, which kind of local affine motion invariance. So it's easy for object recognition, based on a bag of features. Our strategy is very simple. We just first of all, we decide, or we ask user to decide what's the image region of interest. Then we just cut them into patches. We convert the image patch as a whole, we convert them as a set of image patches. So then we're trying to build a model, density model more precisely over the set of image patches. So it's an intermediate solution compared with a direct image method. You track the whole thing, you track the whole image, or you cut them into features. Compared with features, the thing is the image interest, people interest normally, there's no theoretical guarantee you can almost find enough features, and you cannot guarantee this enough feature can across time. So in our case, we just sample them, so it's always, it's flexible. We always have enough data. We have. Okay, so yeah. So the image modeling problem, a region of interest, we cut them into pieces. Then we can build a density model. The density model can be non-parametric, can be parametric, can be semi-parametric. It depends. Okay, the first job I have done, like using image patch representation, is for scene recognition. So what's scene recognition? Give it an image, like you want a computer to tell this indoor or outdoor. It can be acting in some kind of scene category, but I will just use for indoor or outdoors. So all these things, like it's general like a classification problem. It really depends on what kind of image database you play with, right? This actually my work. One was summer intern in Microsoft Research. So I did the photo collection work. So I basically collect this photo from 43 amateur photographers, like just like us, like home users. It's over 5 years. It's from 1999 to 2004. With duplets removed, they can be on a very different size. They can be 2000 pixel by 2000 pixel. They can be 100 pixel by 100 pixel. So it can be taken by digital camera, can be taken by film camera, then you scan it. So it's still not enough data, but there's still. I think the large version class variation is the most challenging for this problem. I hope like maybe in future we can build a very comprehensive database of public and available. So for the baseline. Why I call the two-level approach is I personally like a tactone approach. So this is actually a tactone thing. What's tactone? So from the human perception, in 1970s, people think when they do the texture recognition, they think all the textures are actually a combination of few essential parts. And just like light, light is RGB, just 3 elements, right? It's kind of like any light is a combination, linear combination or nonlinear combination of these two things, of these 3 basic things. So we have unit patches. Then we either supervised do a image patch classification, or we do a clustering if we do not have labels. So this thing will be taken as an intermediate solution, intermediate representation. We call it tactone. Then the photo will be a distribution over these tactones, over this kind of K elements. I personally think like for complex visual recognition problem, tactone is a very good idea, because if you think things directly from the whole photo scale, the things are very different. It's large variation, cannot model them very well. But if you can cut them into local elements, actually, I think the problem is more feasible, more tractable, because it's some kind of any complex thing can be converted into a distribution over simple elements. Okay, how the in this particular work, we choose the supervised version. Why we choose supervised version is we are also interested to detect something with semantical meaning, like a wall or face, not face, skin actually here, grass, some kind of building. So A, C, E, G are the originally cropped image regions, and I just draw some random sample from them. It's purely random. So the B, F, D, E, D, H is random image patches. So you can see these random patches are actually definitely not in the same looking. So, but in that case, in my work, I don't really care about some kind of outlier detection or whatever. I just keep them, because eventually I have a density model. So I just keep all the things in the density model. It's a mixture density model, multi-model, so I don't really care about this. So it's also the size. The size actually is very critical. In our work, we choose 25 by 25, but I do some accuracy like from 15 to 40. It does not really matter, because this thing is something you have to determine. It's like in which scale the perception is more uniform, or it's either exchangeable between different classes.
So the density model is over the different taxonomic categories?
Yes, you can see that. Yes. So given this density model, for any new image, I just scan patches, and each patch will give me a response. I have like 20 different material classes. So each class will give me a grade level image. Actually, it's not 1 to 55. It's a real value. So this is how the detection looks like. So the lighter intensity means higher response, and vice versa. So Yeah, let's talk about how we represent features, how we represent the patches. So this three kind of information: color, texture, and color flat texture. It's a very natural way. And in my experience, I think for like general recognition case, the color space does not make much difference. I just chose RGB, which is the simplest one. And also the typical texture describer will be based on filter banks. So this graph shows how the filter banks looks like. It's actually from the TechTalks paper by Long and Malik. So basically, there are some kind of Gabor filter in different scale, different orientation, different faces, and the DOG filter, Gaussian filter. So another case is Hardick features. Hardick feature is some local statics computed from pairs of image pixels under some special spatial configuration. So these two popular ones. But Hardick feature is not generally used for TechTalks. Okay, so given these features, the first step we want to validate our approach to see what's the recognition rate if we just want to recognize patches, not photos. So the baseline will be just using these features, using nearest neighbors. So I have some supervised learning case. I cut them into training set and the testing set. So here it just give you impression how the different feature looks like. So here, because we have like trees and bushes, right? The color in the color space is pretty much same. So the color feature actually did a very worse job, but this really depends on our artificial selection of material classes. So in my experience, Hardick feature plus color is slightly better than filter banks plus colors. So color information does help. Then in our case, actually adapt method we developed in NIPS 2004, which is unsupervised learning case to this supervised learning case. So it's very simple. You're just using linear discriminant analysis to project this material, this image patches according to the material classes. So it's 20 classes. You project them in a lower dimensional space. Then you fit a Gaussian matrix model within each category, within each material class. Okay, so this is how the thing looks like after when you've done this discriminative density model. So compared with the last figure, I think the performance changed a lot, especially for when you have like more samples. It's like the smoothness. The density model offers you the smoothness in the feature space does help. So I should say the random trial is 5% in the case because you have 20 class classification problem. So this is a confusion matrix.
Can I ask a question?
Okay.
The before and after there, go back previous slide, please.
This one?
So you're talking about the features. I didn't understand what the actual thing that happens after the features is. You've got a mixture model for each class still here?
Oh, yes. We first project them using LDA.
Well, that's what you had in 2 slides from now. Is that what you're also doing here?
No. This one is just based on nearest neighbors. After we have the feature descriptor, we just use nearest neighbor, Euclidean distance nearest neighbors as a benchmark.
Right. So then do you have another experiment where you have done some sort of a mixture model on class that's not based on the LDA, but some other sort of more, you basically collect up all the examples you can for each class and then train a mixture model for each class, and then you get a class conditional density and use a class spread based on that? Did you
yes, it's some kind of density model, but we try to combine the discriminative information into the class, because here we have labels.
Right, so presumably that buys you something, but I'm just curious to see if you've done an experiment where you compare what it buys you, using the LDA approach to
yes. If you
go,
I believe like any good computer, any good machine learning algorithm should be a combination of generative model and discriminative model. It's really depending on which direction you go.
Right. So I guess my question was, are you going to show an experiment that compares it to?
Yeah, this like these 2 figures show the performance. This figure compared with this figure. So it's a very simple comparison for.
Right. So do you have a third? Maybe you don't have it here, but have you done another experiment where rather than try to do an LDA based?
Yeah, I will show you something else.
You just have a maximum likelihood based mixture fitting. Because this isn't mixture fitting.
Yes, definitely. Yes,
right?
yes.
So you've done it, but
yeah, it's open. I would still think it's an open problem. I will show you some other examples, but not in this talk, later on, because all the techniques are connected. So I will show you later on. I did have some kind of comparison or evaluation on different kind of method. So given this, like we call probability density response map, like real value, like grade level images, right? We just compute some very simple moments feature over them. So the first order moment feature is just the weight, how much the thing exists in this photo, and the first order will be the mean position, and the second order will be the what's area. So actually, we only use the zero order and the first order because our photo does not have a structure. It's it's very messy structure, so the structure information does not have much. So after this, we have for each photo we have 20 multiplied by 3. It's a 60-dimensional 60-dimension signals, or 60 vector, a feature vector, or 60 components for each photo, right? So here we use LDA again. It's the same thing, but here is only difference according to the different thing category. Then, because in this, after you transform the thing into a lower dimensional subspace, now you want to do a classification in terms instead of density estimation. So you can use like a Nielsen-Berkin, K-means, or Gaussian Baker model. This is just very general thing you can try. I want to try some very simple thing at first. Okay. I think this is a very interesting picture. Because LDA, because here is the class number is 2, right? So LDA, the most dimension LDA can give you is C minus 1. So here, every photo, no matter the size, no matter what it looks like, it converts in a 1D signal. So without considering these scaled curves, so this thing actually the histograms are how this one-dimensional signal distributed along the x-axis. So in this case, I just have a very simple way to determine the distinct boundary. I just fit them a scaled version of Gaussian function. Then it's a very naive way, but it's the general way you can try first. You always assume something belongs to a Gaussian function. So the interesting part will be where the yellow bars. So the yellow bar will tell you the distinct boundary is one-dimensional space.
Sorry,
okay.
Maybe my questions don't make sense, but you're getting a one-dimensional feature here. Is this like one of the LDA projections? Is that what this is? How do you get a one-dimensional?
If LDA has like basically 2 steps of PCA, right? So the last step of PCA actually tell you what's the final dimensions. Normally you need to do a selection over the model selection step on how many dimensions you want. But the theoretical bound of LDA can only give you C minus 2, C minus 1. This is the maximum subspace dimension it can offer you. So here C equal to 2. We have only 2 classes. So you can only have one-dimensional signal and no further out.
So sorry. So we're talking about Fisher linear description.
Yes. Here.
So this is successively finding projections which maximize the linear separation of the classes. But these classes now are described by features that are higher dimensional.
Yeah. So
the number of classes is 2. You're saying?
Yes. For indoor, outdoors.
Okay. So you're just doing one projection then? Is that what you're getting?
In this case, yes, one projection. I just show one projection. You can do multiple projections. But multiple projections is not...
But don't you get
does not mean LDA offer you more subspaces. It's like you can train a random LDA, based on bootstrapping and based on random subspaces. So basically, like you select subset of training data or subset of your subspaces when you do the first PCA. LDA is a 2-step PCA, right? At first, maybe we can talk about this later.
Yeah, we should talk about it offline.
Yeah, offline. We can talk about this offline.
LDA and PCA are 2 different beasts, aren't they?
Yes. But you can understand. You can think about LDA is a 2-stage PCA. You compute SVD 2 times. Yeah. Okay, we try. Like some kind of bagging weak LDA classifiers by some randomness. So I won't talk about too much about this thing, but we can talk this offline. I believe that this kind of local random method can give you multi-model. LDA is only optimal for single model densities. So I believe this this randomness can offer you to model multi-model distribution, because my work is always trying to model like a complex density model. So this how the random LDA looks like. Actually, in outdoor-indoor case, all the random LDAs the performance is very good. I mean, based on our database. So the boosting does not, the bagging method does not give you much improvement over our classification rate. But I have some like iron result I won't show you here. But when you do multiple scene categorizations, this bagging method does help. But I won't show you here because I don't think it's very important here. So what can go wrong? So I give you like 2 images, my algorithm make error. So on the left, right? On the left side is a human standing, sitting in front of a curtain. But if you have a close view, you will find the curtain is made of artificial leaves. So algorithm cannot, based on the color and the texture information, cannot tell they are artificial leaves or real leaves, because you can have red color leaves. So on the right side is like we can detect mammals and human skin, but we make a wrong decision over the background. We consider some kind of carpet. So carpet should exist in indoor, but actually it's sand. So yeah, this is my impression about the simple LDA, why it works or why it does not work, because we are building blocks over LDA. So LDA actually did a very it's simple, but it did a very effective work on the feature selection. We have like a distribution over these 20 material classes. So LDA automatically tell you which class is more important when you do a certain classification task. Let's see, human can be either in outdoor or indoor, so it's not quite relevant with this when you do the indoor-outdoor classification. But sky, water, maybe they make much difference.
Can you go back to the confusion matrix that shows what you
Okay, yeah, definitely. So, yeah, I just showed you like bush is very easy to be confused with trees, and the carpet is very difficult to measurement. I mean, in this like a standard appearance modeling thing, the carpet is not a well formulated task. I would say like it's a really difficult task when you try to recognize carpet. For human face or whatever, maybe more structured data, more structured visual pattern is easier.
Okay, thanks.
Okay, so yeah, we can talk this later on. Okay. So talk about the database. There, in my opinion, there's 3 different kind of database. Our database, I cannot show you too much about our database. It's like for some reason. So and also, Kodak database is not public available. The 2 works in the Kodak database I should mention. One is by Picard in 1995. It's based on block-based method. It's cut each photo into like a 4x4 blocks of 5x5 blocks. It doesn't really matter. So the scene category for the photo, right? So you classify this. You just treat these blocks as representation for indoor blocks or outdoor blocks. Give a new image, you cut them into blocks, and for each block you make a nearest neighbor classification. Right? You will decide this block is indoor or outdoor. Then majority voting will vote this image go to indoor outdoor. But the problem is, as stated from Low's paper, this performance highly depends on the duplicates. They have actually a lot of duplicates. They select the image like one by one another. So it's highly dependent. And also, I believe the blocks is not the right way to go because it's still too big to be modeled elegantly. Another thing is like a cultural database, which is widely used. But the cultural database is taken by professional photographers, which make a lot of difference. All the images are very color saturated, and also you have a nice structure of the photo. So I think it's easier for. I should really try my algorithm over that. I think it's easier database. So it's not a very fair comparison because everyone working on everyone working on their own database, they do not share the database publicly. So it's just in terms of numbers. Our number is not that bad. It's one of the best, I would say. But I'm not confident to say this thing is the best because there's no comparison, fair comparison. So yeah, I would also say this should be supervised tactone or unsupervised tactone. So actually, from Malik's paper is unsupervised by clustering. So there's another interesting paper using like Bayesian hierarchy models to build this intermediate representation, which they call SIMS, which is like comparable to the taxon with much more complex techniques. But I would really want to try in the future to see this complex model does improve our reckoning rate or not. So actually, the most popular database I would say is Pascal from European Union, and also MIT. They have a large database. There is a lot of manual annotation. I still believe some kind of human annotation, like you teach a computer by showing them by example, is still quite useful. You cannot just do purely on the supervised learning case, because it's I think it's somehow tricky. So of course, a good trade-off will be somewhere between. So we cannot show computer a lot of examples. We can show them few examples. Then make a computer have algorithm to generate these few examples. Generate them to over bigger and bigger space. So eventually, okay. So this is just 3 frames of the video I showed before. So I just want to make sure you know so the image region in the red rectangles are the foreground, we call object. So then the image region in the sign rectangle, we call it background. So you can see actually, when you cross the image, all the things change dramatically. So this, you have to train something online and make them adaptively in the temporal domain. Okay, so here it's the same game. So we present the non-object appearance as 2 bags of patches. So we just scan them and throw them into a bag. This bag belongs to object. This bag belongs to non-object. It's the surrounding area over the object. So we then just use this, bag of patches as the standard training set for binary classification. We determine which is foreground or background, or object, non-object. But we do not have a hard decision. All my decision was continuous. So the key issue is how you build the model adaptively. Okay, this is very easy. So, I just scan the image patches within these rectangles. So for the comparison, I use evidence data. So I also use the same feature representation. So you can really tell what's the difference of algorithm, not the feature representation, not the feature descriptors. So here we go. So after this, our method does not have any constraint on the training set, on online training binary classifier. You can use whatever you want. So I personally tried 3 categories. One is the KNN, which can be considered a nice general benchmark. And also some kind of dimension reduction, because it's supervised learning, you have labels. It's some kind of supervised dimension reduction plus KDE, or you can use Gaussian mixture model as well. But here it's just a simple case, we use KDE. It does not make much difference. The third category will be we just use SVM, super vector machine. But you can use anything else, like boosting or decision tree, whatever. Given the data, just train binary classifier is a standard machine learning problem. The case is in our belief is for different data, you may want to play with different kind of classifiers because every classifier has this advantage, disadvantage. But our algorithm does not have any constraint on these classifiers. You can use whatever you want. Okay, so all these classifiers used, I convert them into a confidence map. So not only a binary label. I do not use the binary. I use the confidence map. I count them I scale them from 0 to 1. So this is the image region in time t-1, and then I use the model up to here, not directly from t-1. It's model up to t-1. I have a continuous temporal adaptive appearance model up to t-1. Then I apply them into the time t, scan the local region, nearby region. So this is a response map. The top right corner and the left bottom corner, they're actually same thing. That one I show you in 3D mesh. 3D, you have a 3D surface. So this thing I show you intensity maps. So hair intensity means lateral intensity means hair response. So given this surface, we use like a standard way, like a mean shift, which is a gradient descent map algorithm. Starting from the location, object location at t-1, you just do some gradient search until you find the next nearby mode, which contains the hairs, the sum of the confidence. Then you get the new location.
So nearby I'm missing the big picture here.
Okay.
Nearby in space, you're trying to map.
Okay. Yeah, I have assembled pictures, right? I sample like image patches, but each patch I know where the location it is, right? So I do the classification over these samples, patch samples. But then each sample will get a confidence value. Then I remap the confidence map into the image coordinates. So you get a 2D, or you get a 2D response map or 3D surface. It's the same thing. It's a gray level image with continuous values, not discrete values.
And this is over taking a step back. So you've got 2 frames. Am I getting this right?
I just show you how the 2 frames, but our model is trained up to t-1. It's a integration procedure.
Okay.
I will show you later on how the model updation.
I guess what I'm missing is so there's some temporal structure here, and I didn't get how you're taking advantage of the prior knowledge that you've got these objects that are moving in certain ways. And
no, I do not assume anything.
Common filter or some sort of dynamic model.
No. It's purely based on appearance, but it definitely can be integrated with that one. My work is purely based on, is it possible we just learn the appearance? We do not assume anything. I will show you later on with another example. You can have a general filter, but you cannot guarantee general filter will work.
You're trying to find,
no model.
So for each region, you're trying to see where did that region go in the next frame?
Yes, somehow like that, yes.
And you're doing it just, so you're not making any assumptions about these
assumption
rigid
at all.
bodies or translating?
Yeah. No assumption at all. No, only assumption is this thing are visually distinguishable. We can tell the difference, and I hope computer can tell the difference as well. So this is the only thing I make, only assumption I make.
So you have 2 categories. So this is a batch method because you're taking your training data from the things that you have, or so it's not sequential.
It's a sequential.
So how do you define your LDA surface? Once you have training data from the full
I have the online. I build the online classifier at each time step, because my model is temporal evolving. So at each time, my model changes, or my training data changes, right?
So what's your training data over then?
I will show you.
From t to 0?
From 0 to t-1 here, up to t-1, up to from the beginning to current.
What time duration is that in practice? Because presumably you're not running it for an hour, for example.
Yes. Yeah, I would say it's short clips. It's a short clips so far. Like a few seconds, 10 seconds, 20 seconds, something like that. So even when you try to really track something in a feature length film, I believe you should try first have some global structure understanding and cut them into clips, because you cannot guarantee a face will appear in every frame in your sequence. I think this is like a cost-to-fine understanding. We have to cut them into pieces. Then in each pieces we have some kind of further understanding or further information we can get from these short clips. Does it answer your question? So this thing won't work if we do not update the model. It's obvious because everything is changing. So this is, this is our main contribution. It's kind of weird written, but I just give you the ideas. So we call bidirectional consistency check, which only involves distance computation in the feature space between A image patches feature to a bag of image patch features. It's Euclidean distance, it's kn distance computed in the Euclidean space. Okay, so what we check? We check two things when we check data given model, right? We want to integrate new data from the model. So we want to make sure something is not very bad. We do not want to integrate bad things into our model. We want, even, sometimes you make a wrong decision when you're tracking things, but you want to keep the model rigidity somehow with the model rejection, with outlier rejection procedure. So we have two steps. So given each image patches, right, in the newly sampled image, I computed the distance towards the bag, positive bag and the negative bag, object bag and non-object bag, right? We have two distances for each patch. So if these two distances are similar, somehow similar, we will reject them. It's, you cannot make a classification, it's a lot of ambiguity in the classification. So we take them as something we don't know. So we reject them from model. It's outlier or something we don't know. So we just integrate the thing we know in the model. Another thing is it's for trying to make the model compact and also control the rigidity. It's like okay, for all the newly sampled object image patches, right? We compute its distance to object class. Then we sort them, as a list. So we remove the thing on the top of the list and at the bottom list. At the bottom list, with the distance very small, we think there are already a lot of redundant information in my model, so I do not really need them. Another case, on the top of the model, they are much likely to be outliers, because if you look at it exactly in the foreground, actually some kind of images in the rectangle is not a very good representation for the foreground. They can contain some kind of outliers. So very simple. I do not even sort them, just compute the mean and the standard deviation up to some kind of mean plus deviation and below mean minus deviation. I will cut them out. So another thing, it's general task. Here is very simple because our model and data can be switched because it's just patches. It's just samples of patches. So I check model given data. It's more like I adapt my model towards the data, towards the current data I use. But I do not make weight them using some kind of continuous weight. I just convert them into a sampling rate because I have to sample out some kind of patch. I cannot just integrate new information, new patch into my model without reject anything, without resample something out, because this thing will be eventually very big. You want to keep them compact and so yeah, it's easy. It's just we convert the distance in another way. We just for the foreground patches in the back patch in the back we model the distance towards the foreground patch newly sampled. So we compute the distance, how likely compare them with a new observation. If they much like new observation, they have higher chance to survive in the resampling procedure. So all this thing can also be considered as somehow similar with particle filtering.
That's problematic for occlusions, right?
What?
That's problematic for occlusions.
Yeah. So I need to show you the videos. I have a lot of videos, 9 videos, not too many. This is a sequence tracking a car in the intersections from a surveillance camera. So this car actually does not have a very big non-rigid motions. So this is from live data. I do not make any, I downloaded this data from a website in Germany. Another I believe is more interesting. I believe it's more interesting because I think it's harder than the former problem. I use the data from Arvidan's paper because I think Arvidan's paper is one of the best, one of the two best. the still art. So I compared this result I show you is something beyond his result. I don't know his tracker will work in this way or not, but I think it's a hard problem. Maybe you want to see it again. So the car has a self-rotation and a large illumination changes, and also the first part is somehow occluded by the bus, and also it's separated.
Following on Michelle's question, do you have any examples that have occlusion in them? That have two objects that overlap or come in front of each other? And
so the women that were walking next to each other was the one with the white
Yeah, if you like, you have, in that case, you have to some kind of like a switching models. Yes, you want to track like two objects with occlusion. You must model them like in a higher level to see. Our model is just based on appearance. We can track things with like a challenging appearance, but you can certainly build something over it. There's a lot of literature discuss about it. When you try to model multiple objects interacting each other. Yeah. So actually, my advisor has like some paper like in the past with his former student. They have a very famous paper about talking about data association model. Yeah. But okay.
So then I had a question. So it's hard for me to interpret the quality of your results because when I think of what I've seen years ago when using a generalized common filter approach, it would take simple cases like this, and my impression is would do just fine.
No, I don't think so. In general, I don't think so, because Kalman filter or whatever particle filtering, you need to train a dynamic model. You need to train a dynamic model beforehand. It means you need to train something which is similar to the testing data, but it's generally not available.
So your strength here is that
I don't make any assumption. I just simple non-parametric model for appearance and maintenance.
So then what do you give up by not making those assumptions?
What?
So then what do you give up by not making those assumptions?
By what? Sorry.
So your advantage over, say, generalized common filters, common filters you need to rigidly specify.
Okay, I show you. I have another example exactly answer your question.
Okay.
Yeah, I will show you later. Okay, I exactly answer your question. Okay, this blah blah. I compare with two of CGR, I believe. It's ICC our paper, CVPI to our paper. They have some like. I think in general the result is comparative because tracking case is like you don't have ground truth. You just see you track it or not. I would wish like in some case we can have some like public available with ground truth, but it's not easy. You need label things in your frame. It's not a very easy job.
Could you go back to the part where you were doing the rejection things?
Okay. Here or here?
Yeah. So in the people walking video, when you cross a background with grass or something to a building, so when you have a background changing, how does this rejection thing work there? Because any new thing it will take it as outlier, right?
Oh, we have a long term, yes, but we do not. It's somehow like it's here. Actually, it's here. It's here. It's like a given model, given the current model. You check the data. You control the model rigidity. That's not. We must include new information. It's for sure, but we just don't want include information too fast or something. It's based on distribution, right? So let's say in the newly sampled image, you have a lot of like this kind of ground. So when you make a list, when you make a distance list, there will be somewhere in the between. So this thing some will guarantee you will integrate them into your model. Only retrieve something which is very unlikely on the top of the list or on the bottom of the list. So you guarantee.
So the case I'm thinking about is in the background, rather than being uniform, is slightly textured, or like if you're crossing a normal street in downtown.
But no structure, no texture is also another kind of feature, right? The feature is 0, 0, 0. In my case, it's histogram oriented gradients. I mean, all these methods I cannot guarantee it will work for any video, but I show some like I think it's challenging videos. I cannot guarantee. You have to, in the long term, it's something like about this. You have to build some detectors. You use the detector interactively. You have to use some kind of detector which have some human knowledge. You then use the detector to cooperate with your tracker. So it's no I cannot theoretically guarantee this will work for any sequence, but I think the video I show you is not trivial. At least for computer vision people, I don't know I can persuade you or not, but it's my video. Okay, this is an example, a close view how the difficulty of tracking is we want to avoid drifting. Drifting is once you make a wrong decision, you cannot come back. But our case, this somehow answers the question. We have a nice combination of long-term observation and short-term observation in our, even it's very simple, but it's effective. So actually, you have a drift. This is the only drift I found from these 4 videos. I wish I can try more videos from like a Hans paper, but Han was something on the business. He cannot give me the data now, but I can try later, definitely. I want to apply my algorithm to the still out. They computer vision people think the video still they provide is challenging. So I want to try on the challenging videos. So then, because the model you have long-term observation, you can actually drag them back. So this is how you call it a robust tracker. So if you cannot avoid drifting at all, you cannot avoid drifting totally. It's, but you try to build something which is robust, where you can drag you back. It's a nice combination of long-term observation and long-term observation. In our model, MSR is non-parametric. You can actually control how rigid the model it is, right? You can, you can control the thing. You can actually control it, but I do not control it. I just use like a 1.5 times of the standard deviation. Okay. And I'll show another one example. It's the same example. I talk them 0.25. It's 2.5. It's not problem 3. It's the same. It's the same. But this is more like a computer graphics project. So computer graphics people always want to capture people working in one environment and then try to extract the foreground and put them into another background. So it's typical like computer animation or whatever. You can capture something in the blue screen, then convert them very maybe flying on the sky or something. So it's cheaper. So I was actually want to try to solve this problem automatically, but I warn you that this is not. I would say I can demonstrate ideas, but I cannot guarantee it's like a perfect something. This problem is extremely hard. It's extremely hard. It's for the computer graphics, I compared the Cigar papers, right? Cigar paper in 2004, they have 2 papers according how you do this thing from images. Then in 2005, they have 2 papers talking about how to extract foreground from a video, like working dynamic foreground from a dynamic video. Not dynamic. In their case, the camera is fixed. So in my case, camera is, I follow a person, so camera is moving. I do not make any assumption except appearance. So, okay, so only difference, there's 3 differences. This is like how I sample images. So before case, I only sample patches over a small region.
Question. Okay. So when you say you don't make any assumptions besides appearance, don't you have some assumptions about the rate at which your models can evolve over time?
Yes. This is it's not assumption. You have to, I cannot say my model is parameter free. It's not parameter free. But I try I just use I do not tune them much. I just 1.5 standard deviation is I just put them there. It works well. I don't know theoretically how we can do this thing better, but I think about this problem. But here just it's somehow like very simple implementation. It's about the implement details. But I don't think it's affect with high level ideas. So this is how I sample images. So basically, it's somehow adapt to the image complexity. So some regions are very complex and much more textures. So I will sample them more densely. Probably this image are oversampled, I would say, because how you determine how many image patches we see is enough for your sample. Though I cut them into image segments, and then sample per image segments, I guarantee each image segment has right amount of repetitive image patches. Then I try 8 configurations based on different matching criteria, based on different feature descriptor, based on different sampling method, like image sampling direct from image, different strategies. Okay, this example showing in the, where I'm from Hopkins, so I had to do something with medicine. So this is from a surgery sequence. So I rested 2 images. Now here is not for tracking. It's just I map the surgical tool in image on the top to the bottom. So this is a random color encoded. The color segmenting looks like. I make a decision over these random colors, right? So on the top is I give the list. I label them how this is the foreground, this is the binary. Then algorithm can automatically generate the bottom thing, the binary mask, to map the surgical tool from one to another. This is not tracking yet, just a mapping, just to demonstrate the idea how you can use the image patching model to label image segments. So I won't talk too detail about tracking, but it's very similar to the former case. It only has 3 extensions. The first one talk about segment the image into chunk of image pixel and make a decision over pixels. So the decision procedure is very simple. It's just an aggregation procedure over the response, the confidence values from the image patches you sampled within each partition, within each super pixels. I just use mean and media. These kind of simple operators. And also, one thing more about on the model updating procedure, the appearance model updating, I plug in one thing which is called random partition, because I believe in this case it's like we have too many samples. We have thousands of image patches over the frame. But in the former case we have hundreds. We have thousands and thousands. So we want to resample them. We want to kick out the redundant information. So we just run random partition algorithm. Yeah, we can talk about random partition algorithm in detail later. So there will be some kind of large partition. And large partition means they have many image samples, and some kind of small number, small partitions. So small partition, they should have higher resample rate, means they have more chance to live in the back. And the bigger partition means they have a lot of redundant information, so we can kick out a more percentage of the unit patches. So other thing can be done with very simple computation. I will show you the video. I cannot say it's perfect. It's definitely not perfect. Also, another thing I should mention, because I can map one image to another. So in the tracking case, I do not guarantee. I don't need to track it from time t-1 to time t. I can jump. I'm not sure I have enough time. This is some of my own work. The first one is will be this year SML. We have a general clustering method to solve the intrinsic ambiguity of sub-theory clustering, which we use for a toy case for a video segmentation, video shot segmentation. So this is my point. When we have a big movie, we try to find the structure of the movie, cut them into pieces. Then in each piece, we should do something adaptively. So this is the feature or characteristic of the temporal feature, temporal signal. So another paper is another tecton-like approach for articulated action recognition, which is, but the implementation is totally different. Okay, to answer your question, I show you the example of the 3D face tracking. I first show you this one. I show the robustness but not accuracy. Because I'm really bad visualize this thing. I plug this 3D model directly overlay on face. You cannot tell the big appearance changes. But you can ask this person. This person is in Google. You can ask him. He will tell you what kind of making face he was when I was trying to tracking his face. He's like a lot of a talking face. We do not track the face as a rigid body. It's definitely deformation, but we try to kick out the outliers. We consider some kind of features. They have both non-rigid part and the motion and the rigid emotion. We kick them out. So here, actually, I compare this thing to the particle filtering. I'm not sure you are familiar with particle filtering. Particle filtering is the extension of Kalman filter. Kalman filter is optimal for when you have single mode, right? Single mode Gaussian distribution. Particle filtering is like you have multiple mode. But particle filtering has a big problem. Is one thing is you need to train with a very similar thing. It's not generally available. When you want to track something, you cannot guarantee you can find a very similar thing. You will label them. You will tell them how the dynamics looks like. It's no guarantee. Another thing is in the high dimensional space, it's a mess. So our work is actually using RANSAC. I'm not sure if you're familiar with RANSAC. We're using RANSAC to sample hypotheses directly from the image observation and feed them into the particle filtering framework. Particle filtering actually are similar to my model updating process. It's basically a likelihood evaluation and a resampling. So I was trying. The point I want to make is trying to have some bottom-up and top-down method. So you have some kind of observation. If you can sample something directly from the observation, make use of it. So I have a few slides to tell you how this thing looks like. This is a framework compared with particle filtering. I think it can be okay. So this is the red dots are my sample. My hypothesis is sampled from noisy image data. The likelihood value is much higher than the particle filtering thing. Particle filtering is basically a dynamic model plus diffusion model. I think in Kalman filter you have to have this dynamic model as well. So it's the same thing. If your dynamic model does not work well, it's completely a mess. And also it's not easy for, in my appearance, it's not easy to train a dynamic model. Okay? To train a dynamic model for an unconditioned video frames. Not sure. We can talk about this later.
Should we understand this graph? This is likelihoods on the y-axis and frames on the x-axis. But what?
No, it's not frame number. It's particle numbers. X-axis is particle number.
If we could maybe just summarize it.
Okay. Yeah, I will just summarize. Okay. Okay, summarize the three topics I taught actually the same way. So first one, I just use a proposed image patch-based representation for scene recognition. Then I extend this patch-based representation into temporal domain for tracking with some kind of simple extensions. The last case I show is by adding some kind of adaptive sampling method, we can try to solve a very complex computer vision or computer graphics problem, which has much higher appearance complexity. So the computational aspect is, I would say, it's very simple. It's very computational. It's very simple. It's non-parametric. It's easy for parallel computing, and the random partition. Then you combine them together. It's guarantees the global optimal. So it's and also okay. The KN need a better implementation, but fortunately there are some kind of ARM papers. In this paper, I just use some naive way to implement the KN. But when you have extremely large numbers of samples or exemplars, we have to use maybe some tree model, make them hierarchical, so you trace the thing computational very efficiently. Okay, I would like to thank my collaborators with my co-author of the paper. Yeah. So, thank you. So.